In this video, we're going to consider a different kind of statistical distribution that we can use to simulate whether or not individuals reproduce or not, and exactly how many offspring they reproduce. Now, in our exercise, we talked about the panda, and we used a simple kind of equation that generated information about whether an individual reproduced or not. And our key assumption is that if individuals did reproduce, they reproduced just a single offspring. Now that might work okay for the panda, but for a lot of other organisms that just won't do. And so in this video we're going to talk about a different kind of distribution that you can use to simulate the number of offspring. I've clicked on the sheet called Poisson, and that is the name of the distribution that we'll be using. We certainly encourage you to find some good reputable sources and learn about the Poisson distribution in more detail. Here we're just going to try to give you a feeling for what the Poisson distribution is. If you've looked at the binomial spreadsheet and have gone through that video with me, you might remember that the binomial distribution is controlled by two parameters: the number of trials, and if we bump this back up to a more meaningful number like 5, and the probability of success. And these are called the model parameters. So these are the parameters of the binomial distribution. If we change these entries, we change the shape of the distribution itself, and you can see that reflected over here. So the binomial distribution requires two parameter inputs in order for you to know what the graph looks like. Well, if we click on the Poisson sheet, the Poisson distribution is controlled by a single parameter called lambda. And you can enter any positive number here in cell B3. And let me just show you how the Poisson distribution works. In cell B9 we're going to insert an equation and we're going to find the Poisson distribution. So let's find anything to do with Poisson, and here it is, Poisson.dist. This particular function has 3 arguments. So here we're asking, what is the probability of an outcome of 0, that's called x, given this mean, and that mean is lambda. And for our demographic stochasticity exercise, that can relate to the birth rate. So if we said pandas have, on average, a birth rate of 1.3, then we can say that we can ask, what is the probability that a female that gives birth will have 0 offspring, given the mean number of offspring across the whole population is 1.3. So let's enter cell A9 as the first argument, and for the mean we'll reference lambda, which is stored in cell B3, and we'll anchor that. And this third argument asks, do we want the exact probability, in which case we'll use the words false, or do we want the cumulative Poisson probability, where we would use the word true as the argument. We're going to start with the exact probability, and so we press OK, and Excel returns a value, and as we pull this equation through, then we are generating a Poisson distribution where we can return what's the probability of 0 offspring when the average for the population is 1.3. The answer is 0.27. What's the probability of 1 offspring? The answer there is 0.35, which we would expect, right? Because 1 offspring is pretty close to this average, and so we're going to expect that we have approximately this number. And that will become more clear as we graph this. So we can just simply include this graphic here, and then let me go ahead and change the axes. Here I've entered the word probability and I changed the axis so it starts at 0 and ends with 1. And then along this bottom axis is the number of offspring. And let me fix this reference to the number of offspring because it should start with 0 and then head out to 11. So it will select the graphic and then we'll choose select data, and for the horizontal axis we'll choose the series and update our graph. And now we have the Poisson distribution. The Poisson distribution is controlled by this single parameter. So if we change this to a different number, then you can see that the Poisson distribution changes as well. So it's controlled by a single parameter called lambda. And this parameter changes where the graph is centered as well as how spread out the data are. And a particular characteristic of this particular distribution is that the variance of this distribution is exactly matched to the mean. So the higher this number is, the more variable we become. So let's go back to a population of where the birth rate is 1.2. Under this condition, the probability that a female that gives birth will have no offspring is 0.301. The probability that a female will have one offspring is 0.36. The probability that a female will have two offspring is 0.217. So you can see, though, that even on average, if I change this to 1, there are individuals that have no offspring, and there are individuals that have 2, 3, 4, and very, very small chance of having these much higher numbers of offspring, but there is some chance that that will happen. Notice also that the sum of these probabilities is 1, and you just need to make sure that you extend your possible outcomes down far enough so that you are integrating the sum of those different bars is equal to 1 exactly. Now, how can we use this distribution to assign a random number of offspring to a female? We know that a female has to have an integer number of offspring. She can have 0, 1, 2, 3, etc., but she can't produce 1.2 offspring. Well, we can use the cumulative Poisson to do that. And in the cumulative Poisson, we're going to start our entry with 0. And if you've seen our other videos, you'll notice that we're going to just use the exact same Poisson dist function. We're going to ask what's the probability of 0 offspring given the mean number stored in cell B3. And here we'll enter true for cumulative. And as we pull that down, you can see that we are just accumulating our results. So 0 offspring has an exact probability of 0.31, and the cumulative probability is also 0.31. When we get to 1, the probability that an individual has one offspring is 0.36. The cumulative, however, is actually adding a 0, the 0 possibility, as well as the possibility of one offspring. So it's adding 0.301 and 0.361 to give 0.663. So each of these values is just the sum of the probabilities, so anything of that value or smaller. Now, we can use this, this vector here. It starts with 0 and it ends with 1. And we can use this vector to draw random values, random x's, from the Poisson distribution given a particular lambda. And we'll do that by entering a random number in cell B4, and then we're going to use a lookup function in Excel. Let's find the lookup function. This is just lookup. This function has two kinds of forms, and we're going to use this form that has the lookup value, the lookup vector, and the result vector. So we're going to look up this random number in this cumulative Poisson distribution vector. So I've selected cells C8 through C19, and the result vector is going to be the deviates, the variables that we can draw from the Poisson distribution. And you can see that Excel is returning a particular number of offspring. If I press F9 in a PC, we're going to generate new random numbers, and you'll notice that this is the offspring. They're always going to be a whole integer number of individuals. This is exactly what we need if we're simulating the birth of individuals per female. So it stops us from producing fractions of individuals. Now what's happening here? Let's take one example. Here's the random number 0.63. The lookup function is finding this value in this ordered array. So this vector starts with 0, ends with 1. It finds the value 0.663, which happens to be right here. And let me choose a different random number that's not quite so exact. 0.820. It finds it, it's between these two values, and it returns the value associated with the lower of the two. That's because we've offset these two arrays a little bit. And if we do this and repeat this process and take lots of random numbers, we'll see that over the long term, when we average our number of individuals, we'll end up with about 1.2 as the population average. Let's try that. We'll have our females listed down column E, and we'll just let there be a whole bunch of females. Let's stretch this out to 150 or so. And each of these females is going to have a random number. And that's RAND, open parenthesis, close parenthesis, and we'll copy that down. And now we'll compute her offspring, and we'll use this cumulative Poisson distribution, and we'll do the same lookup function. So let's go find that lookup function once more. We're going to look up the random number associated with that female in the lookup vector. That's the cumulative Poisson distribution, and the result vector are the variables that we can draw from the Poisson distribution. We need to anchor both of these vectors, so we'll do that. And then press OK, and then click this through, and now you can see that we have 150 females, each of them producing an integer number of offspring. Now let's find out what the average is for this population, and we'll just use the average function, and we'll select all of our individuals and press OK. And what you should see is that this average matches the lambda that we've specified in cell B3. So if I change the lambda here now I'm drawing from these random deviates from a Poisson distribution where lambda is 1. And if I press F9 and get some new random numbers, you'll see that it's hovering around 1. In some cases, we get a little bit higher or lower than we expect, and that issue would go away if we extended the number of females out to 10,000 or so. So let's just try one more example. If the lambda value was 3.1, it's more likely that individuals will have 3 or 2 offspring. 4 offspring is possible too. We see those are common numbers here, and when we look at the average number, it's pretty close to what we've simulated. So that, in a nutshell, is the cumulative Poisson distribution. It's another one of those distributions that is very important in terms of modeling, and we use it to simulate whole numbers, whole integers. In this particular case, we're interested in offspring population. There are other examples too. The 2 other possibilities are the log normal distribution and the gamma distribution.